How did black holes go from speculation to observation? What exactly makes an event horizon a no-return boundary? How can dense mass warp space-time to capture light? For as long as we have been human, we have looked up at the night sky and felt something stir inside us. Under a dome of stars, our ancestors wondered at the glittering lights sprinkled across a backdrop of darkness. The darkness itself, the endless black between stars, was as captivating as the points of light. It was a canvas for our imagination, a realm of mystery where anything could be lurking. In that vast, shadowy expanse, humanity found both fear and fascination. We told stories about the night sky to explain what we could not see, populating the darkness with gods, monsters, and dreams. Even before we understood the science of space, the dark of the cosmos called to us with a quiet, inexplicable allure. As our knowledge grew, the mysteries only deepened. The more we learned about the stars and planets, the more we realized how much remained hidden in the dark void between them. Scientists began to suspect that something incredible might be concealed in that darkness, objects so strange and powerful that they defied imagination. As far back as the 18th century, a few bold thinkers even proposed that there could be dark stars, stars so massive that their gravity would trap even light itself. At that time, it was just a speculative idea, a curiosity on the fringes of science. But it planted a seed, the notion that the darkness out there might hold phenomena more exotic than any myth. Decades and centuries passed, and our understanding of physics grew. In 1915, Albert Einstein's new theory of general relativity provided the tools to describe gravity, not just as a force, but as a bending of space and time. This revolutionary idea hinted that if enough mass were packed into a small enough space, space and time could curve in on themselves, potentially creating a true dark star, what we now call a black hole. The concept was so extreme that even Einstein himself was uneasy. In 1939, he argued that such phenomena were not convincing and likely did not exist in the real universe. It seemed absurd that nature could produce a gravity trap so complete that nothing, not even light, could break free. Yet the allure of that idea persisted. Other scientists picked up where Einstein left off, working out the equations and wondering if massive collapsing stars might create these gravitational abysses. For a long time, black holes remained theoretical, fascinating on paper, but with no evidence they actually existed. Then, in the 1960s, the evidence began to emerge. In 1964, astronomers detected mysterious X-rays coming from deep space, from an object later identified as Cygnus X1, a strong candidate for a black hole. For the first time, we had a hint that something truly dark was out there, not just in our equations, but in the sky itself. Scientists had finally glimpsed a stellar ghost, the kind of remnant left behind when a massive star dies and perhaps collapses into an invisible abyss. Skepticism turned slowly into belief as more data arrived. By the late 1960s, the term black hole was coined by physicist John Wheeler, and these once hypothetical dark stars began to be accepted as real celestial objects. Humanity's fascination with the darkness was no longer just philosophical or mythical. It was becoming scientific fact. In April of 2019, that fascination reached a new height. After decades of theorizing and indirect evidence, we finally saw a black hole, not with our eyes, but through the lens of a globe-spanning telescope network. The Event Horizon Telescope team revealed the first ever image of a black hole's shadow, a glowing ring of light encircling a pitch-black center. It was the shadow of a supermassive black hole in a distant galaxy, 55 million light-years away, its gravity so immense that it bent light around itself and cast a dark silhouette. That moment was a triumph of human curiosity and technology. What once was an idea on the fringes of imagination was now confirmed, captured in an image we could all see. The gravitational monsters Einstein once doubted had proven to be real, lurking out there in the darkness as we always suspected. And yet, seeing that dark center, the place from which no light returns, only made the mystery more profound. We were looking at the brink of an abyss, the edge of infinity. Our journey thus far, from ancient stargazers to modern astronomers, has been guided by a constant, a deep longing to understand the darkness as much as the light. Black holes embody that darkness in its most extreme form. They are the fulfillment of an ancient fascination, objects that are literally made of shadow, places where light slips away and time itself seems to stand still. Now that we know these enigmatic black holes truly exist, the question becomes, what are they like, and how do they come to be? We stand at the threshold of understanding, peering into the darkness, ready to delve deeper. In the silent, invisible pull of gravity, in those cosmic wells that trap light and time, we find the next chapter of our exploration. The darkness beckons us onward, into the grasp of gravity's invisible grip. Gravity is the silent architect of the cosmos. It holds planets in their orbits and binds galaxies together. Yet it works invisibly, felt, but never seen. In our everyday lives, gravity's grip is gentle. It makes apples fall and keeps our feet on the ground. But out in the depths of space, gravity can become a formidable, all-consuming force. Nowhere is this more evident than around a black hole. A black hole is the ultimate gravity well, a deep pit in the fabric of space and time. Imagine space as a stretched sheet of fabric. A star or a planet makes a little dent in the sheet, like a bowling ball resting on it. A black hole, by contrast, is like a lead weight that punches a hole straight through. Its gravity pulls so strongly that anything venturing too close is drawn in, unable to climb back out. The very idea of such an object is mind-bending, a place where gravity seems to win over light itself. What exactly makes a black hole's gravity so overwhelming? The secret lies in how concentrated its mass is. Think of taking a star many times heavier than the sun and crushing it down into an unimaginably small sphere. All that weight pressed into a tiny space creates intense gravity around it. In fact, if you compress enough mass into a small enough volume, you reach a tipping point, a boundary in space beyond which the pull of gravity is so extreme that nothing can escape. Not even light, moving at the fastest speed in the universe, can break free of this grasp. This boundary is called the event horizon, the point of no return. Once anything passes that invisible line, it vanishes from the outside universe's sight. The object itself, the black hole, is not actually a hole at all, but a ball of mass packed densely in the center. Yet it appears utterly black because nothing, not even a single ray of light, comes back out. It is a region of pure shadow. Scientists describe it succinctly. All the mass is concentrated in a tiny region, surrounded by an event horizon through which nothing can return. To better sense how a black hole warps gravity, let's return to the image of space as a fabric. Place a heavy bowling ball on a rubber sheet, and it stretches the sheet into a well, Now imagine putting something far heavier, say a cannonball, on the sheet. It would stretch deeper, perhaps even tear through. That's what a black hole does to space-time. The mass is so dense that space-time curves steeply inward. Near a black hole, paths that light would normally take become distorted. If you were watching from a safe distance, you'd see strange effects. Stars behind the black hole might appear warped or doubled, their light bent like beams passing through a giant lens. In a sense, the black hole hides behind a funhouse mirror of gravity, its presence revealed only by how it bends the light around it. Gravity, which is ordinarily an invisible force, becomes almost tangible near a black hole, sculpting the space around it into a deep, dark well. As one physicist famously put it, matter tells space-time how to curve, and space-time tells matter how to move. In the case of a black hole, the matter has told space-time to curve into a bottomless pit. Despite this dramatic image, it's important to remember that black holes are not cosmic vacuum cleaners, indiscriminately sucking in everything around them. If our sun were magically replaced by a black hole of the same mass, the Earth and other planets would continue to orbit almost as before, albeit in darkness, because at our orbital distance, the gravity would be no different. A black hole's pull is ferocious only very close in. Like any other massive object, it obeys the normal laws of gravity. Objects fall toward it, just as they would toward a planet or star. What makes a black hole deadly is how close you can get to its mass. With a star or planet, there's a surface that keeps you some distance from all the mass. But a black hole has no surface in the traditional sense. You can get incredibly close to that concentrated mass, and the closer you get, the stronger the gravitational pull becomes. So while a spacecraft far away can orbit a black hole safely, one that strays too near will be captured, spiraling past the event horizon into darkness. The extreme density of black holes leads to some astonishing characteristics. For example, a black hole with the mass of our Sun would have a diameter of only about 6 kilometers, essentially the size of a small town. In reality, most black holes born from stars contain a bit more mass than that, perhaps a few times the Sun's mass, but even those would span only a few tens of kilometers across. By contrast, our Sun itself is about 1.4 million kilometers in diameter. One can scarcely imagine all of that mass squeezed down to a ball just a handful of kilometers wide. And yet, that is what a stellar black hole essentially is. Matter compressed to such density that it carves a deep dimple in space-time. On the other end of the scale, there are black holes that contain millions or even billions of times the Sun's mass. These are the supermassive black holes that reside in the centers of galaxies. Despite their tremendous mass, they are still extraordinarily compact relative to their weight. The supermassive black hole at the center of our Milky Way, for instance, is about 4 million solar masses, but it would easily fit inside the orbit of Mercury. A beast like the one in the galaxy M87 is billions of solar masses, yet would still be only about the size of our solar system. In simple terms, black holes are tiny for what they hold, truly cosmic heavyweights, compressed into the smallest of volumes. That compactness is exactly why their gravity can become so intense. You can approach much closer to a black hole's mass than you could to a normal star's mass, and this closeness turbocharges the force of gravity. Scientists point out that while other objects can be as massive as black holes, none concentrate their mass in such a minuscule space. That's what sets black holes apart. Because black holes themselves emit no light, we usually detect them by their influence on surroundings. Many black holes, especially the big ones in galaxies, are orbited by disks of gas and dust spiraling inward. As this material falls into the black hole's gravitational well, it speeds up and heats up, glowing brilliantly. Ironically, the darkness of a black hole often comes with a spectacle of light just outside its border. The gas whirling around the hole, called an accretion disk, can shine so bright that we see it from millions or billions of light years away. Indeed, some of the brightest objects we observe in the universe, like quasars, are powered by supermassive black holes furiously feeding on infalling gas. We cannot see the black hole directly, but we see a telling silhouette, often a brilliant ring or disk of light swirling around an utterly dark center. It is as if the black hole wears a luminous crown that highlights its own invisibility. Occasionally, these cosmic engines also produce jets of high-energy particles that shoot out along the black hole's poles, adding to the fireworks. All of these effects are the byproducts of matter struggling against gravity's grip, heating up and radiating energy just before it crosses the event horizon and disappears. In essence, a black hole is nature's way of concentrating mass so densely that the fabric of space-time caves in around it. It is a cosmic trapdoor, a one-way passage inward. Anything that ventures too close, a drifting star, a cloud of gas, or a curious spacecraft, will be claimed by this invisible grip of gravity. Understanding this gives us a profound insight. Black holes are not supernatural. They obey the same gravity that holds us to Earth, but taken to an extreme. We now know what a black hole is and how it governs its domain with relentless gravity. The next question is, how does such an extraordinary object come into existence? To answer that, we must witness one of the universe's most dramatic events, the death of a massive star. It is in the fiery finale of certain stars that black holes are born, emerging from stellar destruction as ghostly remnants that continue the cycle of cosmic evolution. Stars are the great luminous engines of the universe, but even they are not eternal. In the quiet depths of space, a very massive star lives its life in a brilliant but brief blaze of fusion. For millions of years it fuses light elements into heavier ones in its core, shining fiercely and pushing outward against the crush of its own gravity. Yet one day, inevitably, the star's fuel runs low. In a star perhaps 10 or 20 times the mass of our Sun, this moment is catastrophic. Without the outward pressure from fusion to support it, the star's core begins to collapse inward under its immense weight. In seconds, matter that has burned brightly for ages implodes. Temperatures and pressures skyrocket to unimaginable levels. The core, once a seething ball of hot gas, is squeezed denser and denser until something has to give. At the very instant the core collapses, the star's outer layers are violently blown off in a titanic explosion, a supernova. For a brief time, this dying star can outshine an entire galaxy. The supernova explosion hurls stellar material, heavy elements forged in the star's final throes, out into space, seeding the cosmos with the ingredients for new stars and planets. But what remains behind at the center is the former heart of the star, now crushed beyond recognition. If the star was only moderately massive, its core might survive as a neutron star, an ultra-dense, city-sized ember made mostly of neutrons. However, if the original star was very massive, above a certain threshold, even neutron star matter cannot withstand the gravitational collapse. There is no force left in the universe that can halt the implosion. The core continues to fall in on itself, contracting tighter and tighter, until it forms a black hole. In that moment, a new black hole is born from the death of a star, a stellar mass black hole, invisible and ravenous. What was once a shining sun has become a ghost, an object with no light of its own, marking the spot where a star's light was extinguished. This newborn black hole is a silent remnant. It retains most of the mass of the star's core, now packed into an extraordinarily small sphere. A black hole of 10 solar masses, for instance, would likely measure only a few tens of kilometers across, far smaller than the Earth in size, yet vastly heavier. Space around it is now a gravitational trap. Any remaining gas nearby may spiral in to feed the black hole, or it may be flung away by the force of the supernova blast. Often, nothing obvious is left to mark the black hole's presence. It simply sits in the darkness, a stellar ghost cloaked in its own gravity. These black holes do not emit any light. They can only be found by their effects on other objects. For example, if our stellar remnant has a companion star orbiting nearby, the black hole's gravity may siphon gas away from that neighbor. As the gas falls in, it heats up and shines in X-rays, betraying the otherwise invisible phantom. In fact, the first black hole astronomers ever detected, Cygnus X1, was discovered in this way, by the X-ray glow of a companion star's gas being devoured by an unseen mass. Most stellar black holes, however, are solitary and dark, roaming the galaxy quietly. Scientists estimate that the Milky Way is home to tens of millions of these unseen black hole remnants. Like ghosts, they drift unnoticed among the stars, unless something happens to illuminate their presence. Though born in violence, a black hole's existence after a supernova is calm and rather eerie. The chaos of the star's death has passed, and what remains is an object essentially made of pure gravity. It will persist perhaps for trillions of years, slowly evaporating via subtle quantum effects, but for all practical purposes, enduring far longer than the star it came from. In the meantime, it simply warps space around it and patiently waits for any matter that might wander too close. If the black hole is in a binary star system, it may gradually consume its partner star, or it might lie dormant if it has nothing to eat. One could float very near a stellar black hole in complete darkness. There is no solid surface, no shining form, only the stars in the background swirling oddly due to the black hole's gravitational lensing. In a way, it is as though the star's ghost has a gravitational presence, but no visible body. The transformation of a massive star into a black hole is one of nature's most dramatic metamorphoses. A thing of light becomes a thing of darkness. A creator of radiance becomes an abyss from which no light can emerge. It reminds us that even stars, the powerhouses of the cosmos, have life cycles that eventually lead to an end. But in that end, they give rise to something new, a black hole, which can in turn influence new generations of stars through its gravity and outflows. In the grand cosmic ecosystem, the deaths of massive stars sow the seeds of future creation, even as they leave behind these enigmatic dark remnants. Now that we've followed the birth of a black hole from stellar death, another question arises. What would it be like to encounter one of these gravitational ghosts up close? To explore that, we must imagine venturing toward the edge of a black hole, approaching the event horizon itself. In the next part of our journey, we step closer to the ultimate boundary, the point of no return, and experience what it means to near a black hole's embrace. The journey now takes us to the very edge of the abyss. Imagine that we are approaching a black hole, drawing closer to the point of no return. At first, from afar, the black hole might seem unremarkable, an area of darkness silhouetted by a halo of light from surrounding gas. But as we move nearer, strange effects begin to unfold. Starlight from behind the black hole bends and warps into rings and arcs, as if the sky were being funneled around an invisible lens. Space itself feels increasingly distorted. We are falling deeper into the gravity well, and the pull grows steadily stronger. Yet everything is eerily quiet and calm. In the vacuum of space, there is no sound, only the silent stretching of light and the steady increase in the black hole's grip on our spacecraft. Soon, we reach a region where escape becomes nearly impossible. This is the black hole's vicinity proper. Space is now so curved inward that turning back would take an almost unimaginable amount of energy. We notice that any light trying to climb away from here is redshifted, its wavelength stretched to longer and longer tones. Time itself seems to be behaving differently. Our ship's clocks still tick normally for us, but if a distant observer were watching, they would see our movements slow down bizarrely. The closer we get to the black hole, the more time appears to dilate. Far away, someone would see us as if moving in slow motion, our ship's fall stretching into a frozen tableau as we approach the critical boundary. Ahead of us lies the event horizon, the point of no return. This boundary is not a physical surface. It is simply the radius around the black hole at which the inward pull of gravity becomes irresistible. Once we cross that invisible line, there is no coming back. Not even light can escape from inside the event horizon, which is why the black hole's core appears utterly black. We hover just outside this boundary for a moment, knowing that beyond it, all our ordinary expectations of physics will be upended. It's a horizon in the truest sense, a boundary between the known universe and whatever lies inside the black hole. The space around us is extreme. Light from the outside universe is being contorted into a faint ring of warped images above and below the blackness. Our ship's instruments struggle to make sense of the gravitational distortions. We are in a place where the normal rules of motion no longer fully apply. We have entered the edge of infinity. As we take the final step and let ourselves drift past the event horizon, something astonishing and rather frightening occurs. That final crossing itself, from our perspective inside the ship, feels uneventful. There is no sudden jolt or magical flash. We simply slip into the black hole's shadow. But at the very same time, extraordinary forces begin to act upon us. The gravity at our feet, closer to the black hole, is significantly stronger than the gravity at our head. This difference in pull starts to stretch our bodies lengthwise. In fact, it would stretch every single atom of our being. Scientists have a whimsical name for this fate: spaghettification. Just as a piece of pasta can be stretched, any object, even one as solid as a person or a spaceship, would be pulled into a long, thin shape. If our black hole were a smaller one, this stretching would rip us apart well before we ever reach the horizon. However, we have chosen a supermassive black hole for our voyage, one with a gentler gradient at the event horizon. That means we have made it inside intact, at least for now. Still, the tidal forces are growing stronger with every kilometre we descend, and we can feel the immense power starting to deform our ship around us. Inside the event horizon, space and time themselves trade places in a sense. All paths lead inward now. Our ship is inexorably drifting further toward the black hole's central singularity, the point of infinite density hidden deep within. No force in the universe can stop this fall. The view outside our window becomes stranger by the second. Light from the outside universe is now bent completely around on itself, so that no matter where we look, we see the back of our own ship, or a swirl of light that seems to wrap around us like a cocoon. Ultimately, we don't know what fate awaits inside this black hole. According to general relativity, we will be drawn into the singularity at the center, crushed into the very fabric of space-time. But other theories hint at different outcomes, perhaps a bridge to another point in space-time, or some quantum rebirth. For now, all we know is that we have passed the one-way door. In this silent darkness, cut off from the universe we came from, we have done what countless science fiction stories have imagined, and no person has ever achieved. We have plunged into a black hole. The relentless pull leads us forward into unknown depths. Surrounding us is nothing but darkness, and the dim glow of energies we can no longer escape. It is a realm beyond the cosmic horizon we once knew. Our voyage must pause here, at this juncture between everything we understand and the mysteries that lie ahead. We have journeyed from starlight into shadow, from the edge of infinity to the very heart of darkness. And although our story stops at this precipice, the true ending, what ultimately happens deep inside the black hole, remains a mystery that our imagination must leave shrouded in night. An all-encompassing darkness surrounds us as we slip silently past the invisible boundary of the black hole. In this moment, we cross the threshold that has long loomed before us, the event horizon. There is no marker or flash as we pass through. Nothing announces our entry. One instant we are still barely clinging to the outside universe, and the next we have left it behind. Crossing the event horizon feels eerily ordinary at first. There is no sudden jolt, no violent shift in sensation. Our spacecraft, or our very being, continues its descent as if nothing has changed. Yet everything has changed. We have stepped beyond the point of no return, into a realm from which escape is physically impossible. The knowledge of this finality settles in quietly, like a heavy curtain drawn behind us. At this enormous scale, we realize why our crossing has been so gentle. Although an unimaginably strong gravitational field surrounds us, we feel no crushing weight. In freefall, we remain weightless, not pressed down as one might expect, for everything around and within us is falling together at the same rate. We must be falling into a supermassive black hole, the kind found at the centers of galaxies, with a horizon so vast that its curvature here feels almost flat. The difference in gravity between our head and feet is negligible at this boundary, sparing us from immediate harm. In a much smaller black hole, one only a few times the mass of a star, the tidal forces near the event horizon would already have been lethal, stretching and compressing us violently. Here, by contrast, the black hole's gravity well is so wide that we glide inward intact, at least for now, in these outer regions of the abyss. We know this gentle reprieve is only temporary. Deeper within, even a supermassive black hole will unleash its full fury in time. Light itself can no longer find a way out now. If we were to shine a beam from a flashlight behind us, attempting to send one last signal back to the universe we knew, it would curve helplessly inward. Every photon, every bit of information that tries to travel outward is inexorably pulled back, unable to break free from the black hole's grip. We realize that communication with the outside has effectively been severed. We are on our own inside this darkness. As we peer back towards where we came from, the view changes in surreal ways. The bright pinpoints of distant stars that once surrounded us are vanishing. The outside universe, full of light and familiar constellations, is shrinking into a dim halo far above and behind. It's as though we are looking up through a dark well, seeing the world we left as a fading circle of light. The edges blur and warble due to the extreme gravity distorting the path of those final rays reaching our eyes. There is an uncanny stillness here. Inside the event horizon, space itself is different. We feel no wind, hear no sound, only an oppressive silence, and the steady pull drawing us deeper. Our senses must rely solely on what little light remains from the outside, or any instruments we carry, but even those will soon fail to make sense of what's around us. Time seems to stretch out in this silence. Each moment feels oddly prolonged, as if the act of crossing has introduced us to a new rhythm of time. We notice that our clocks, if we check them, tick onward normally for us. Our hearts, if we are alive to feel them, still beat in a calm, steady rhythm. In our frame of reference, nothing peculiar is happening with time. Yet we understand that this normalcy is deceiving. To any observer left outside, our motions are slowing to an imperceptible crawl near that horizon we just crossed. We have entered a place where time and space intertwine strangely, though from our perspective, we continue forward as usual. Drifting further inward, we pass beyond any light that originated outside the black hole. Ahead of us lies pure darkness. Not just the darkness of night, but a complete absence of any photons or signals. It is a void in which our eyes find nothing to latch onto. We might turn our gaze to our own vessel or body, just to see something familiar amid the emptiness. We can still see ourselves by the faint illumination of our instruments, but beyond that, nothing external remains visible. The concept of direction begins to lose its usual meaning. Outside of a black hole, if you look up, you might see sky and stars. If you look down, you might see the ground or the cosmic abyss ahead of you. Here, down, inexorably points toward the singularity deep inside, a direction we are compelled to follow. Up would be back toward the event horizon and the universe we left. But even looking up only shows a dwindling patch of light, increasingly red-shifted and dim. Everywhere else around us, the view is swallowed in darkness. We feel a profound sense of isolation and wonder. We have literally left the known universe behind. No outside force can reach us now. No message can escape to tell our story. The event horizon is sometimes called the ultimate one-way door, and we have closed that door behind us. A gentle awe settles in with the realization. We are explorers in a realm no one has seen, and whatever we observe or experience here will be for us alone. It is humbling and mysterious. We carry the weight of that mystery as we journey further in. Floating in this emptiness, we reflect on what it means to cross such a threshold. This boundary we traversed is not a physical surface at all, but a region of space defining where escape velocity equals the speed of light. On one side, it was theoretically possible, if hardly practical, to turn back or send a signal out. On this side, not even light, the fastest thing in the universe, has the speed to break free of the immense gravity. We are now bound to the fate of whatever lies inside. Slowly, it dawns on us that even though we do not feel it yet, the forces at play here are growing stronger with each passing mile we fall inward. The smooth passage across the horizon won't remain gentle. We have entered the black hole's dominion, and deeper inside, the pull of gravity will intensify beyond anything we have encountered before. The event horizon was merely the gateway. Now the true journey into the extreme begins. Behind us, the last images of the external cosmos become ever fainter. If we pause for a moment perhaps using thrusters to orient ourselves, and look back at the way we came, we might see a strange sight. The light from the outside world is so distorted that it wraps around, forming an eerie glow at the rim of our vision. We realize we can almost see parts of the universe behind us in multiple directions due to the warped space-time bending light. It's as if the black hole's gravity lens is allowing us a final glance at the outside from different angles at once. The stars might appear smeared into arcs or rings encircling the darkness. This effect is mesmerizing and disorienting. We remember images scientists have shown of how a black hole warps the view of accretion disks or stars behind it, twisting them into surreal shapes. Now, we are experiencing a version of that firsthand. The gravitational field we are in is so intense that it bends the very path of light around us. The outside universe, which should lie behind, seems in some ways to wrap around and above, as gravity deflects those rays into our line of sight. All the while, that ring of light overhead grows dimmer and more red-hued. Wavelengths stretch as they struggle to climb out of the gravity well, making the light that does reach us weaker and redder, a final sunset glimmer of the universe we left. We continue our descent, letting that last glow shrink further. There is something solemn about watching it disappear. It's akin to watching the sun dip below the horizon at dusk, knowing night will soon be complete. Here the sunset is of the entire universe setting behind the curvature of space-time. The vault of stars and galaxies we once knew has now faded to a memory and a faint whisper of light. We face forward, or rather downward, into the black hole's interior, where new and strange sights may await. Or perhaps nothing at all, but endless dark. Yet even in darkness, our journey continues, guided by curiosity and the laws of gravity that pull us onward. In the absence of external light, we rely on intellect and imagination to fill the void. We recall what physics predicted for this environment. We know that inside this event horizon, all paths lead inexorably further inward. Space and time here are not as we are used to. The very notion of forward now effectively means moving toward the center, and that is as unavoidable as moving forward in time was outside. We cannot stop our fall any more than we could halt time itself. This realization washes over us gently. It is frightening in one sense, yet oddly calming in another. We surrender to the flow of space-time, much like a leaf carried by a current. With the event horizon now behind us, we cross into a domain where human intuition falters. No eyes have directly seen this place. No hands have touched it. It exists for us now as a combination of observation and the mind's eye, guided by physics. The emptiness has a texture of its own, perhaps the distant remnants of radiation, the whisper of starlight that fell in long before us, or the faint glow of particles heated during their plunge. If our instruments are sensitive enough, they might pick up a faint background hum of energy, possibly relic heat from annihilated matter, or the faint afterglow of the cosmic microwave background dragged in. But to our human senses, it is dark and still. Our voyage across the threshold is both literal and metaphorical. We have crossed from the realm of known physics into the unknown. Outside the horizon, we could rely on centuries of astronomical observations and well-tested theories to predict what might happen. Inside, those theories still guide us, but they point toward a breakdown of understanding the closer we get to the center. We carry that awareness with us, At some point ahead, perhaps not too far now, our current knowledge will reach its limit. But for now, as we drift downwards, we observe everything we can, savouring the experience of being in this extraordinary place. The black hole's gravity continues to tug us along a one-way journey. We think about how this very region we occupy is hidden forever from the outside universe. To anyone watching from a distance, we are already effectively gone, just an image fading on the event horizon. In a sense, being here is like being frozen out of the rest of time's story. We have our own timeline now, separate from the cosmos beyond the horizon. This raises a gentle, philosophical wonder. What does it mean to experience time and space so differently? As we cross the threshold, we realize we are also crossing boundaries of understanding. What does reality even mean here? Questions float through our mind calmly, without panic, as there is a surprising peace in this isolation. Strangely, though we are in one of the most violent environments in the universe, right now within the smooth space just inside the horizon, it is tranquil. It's the calm before deeper extremes, a silent interlude given to us to contemplate where we are. We take this moment to breathe, if breathing is possible, perhaps only metaphorically, if our journey is imagined rather than physical. Either way, there is a pause as we move steadily inward, a moment of reflection. We have crossed the event horizon. We have entered the ultimate unknown. Ahead lies the rest of our plunge into the maelstrom of the black hole. The adventure is truly underway, and we continue, slowly and steadily, into the darkness ahead. Deeper inside the black hole, the calm eeriness begins to give way to something more intense. We have been drifting inward in silence, but now we start to feel the subtle signs of change. The gentle ride is ending. There is a growing sense of pressure, not like air pressure on our bodies, but a pressure on space itself, as though the fabric of reality is straining around us. Distances that once felt ordinary now feel distorted. The pull of gravity is strengthening with each passing moment, and it isn't uniform. We notice that different parts of our vessel, or our body, if we imagine ourselves unprotected, are not being pulled equally. The far side of us, slightly closer to the black hole's center, feels a stronger tug than the side farther away. What was a negligible difference earlier is becoming noticeable. Space and time are beginning to bend in earnest, and we are caught in their distortion. We attempt small motions to test our environment. Perhaps we fire our thrusters lightly, trying to change direction or slow our descent. The response is alarming in its futility. We can turn a little. We can perhaps manage a slight sideways drift. But nothing we do alters the fundamental fact that we are continuing to plunge inward. It's as if the space around us is funneling us along a fixed path. No matter how we try to steer, we keep being drawn toward the unseen center. This isn't like normal space where a powerful engine could let us escape or change course drastically. Here, altering our trajectory is like swimming against an impossibly strong current. We expend energy, but the current carries us along regardless. We realize that inside this black hole, the very concept of moving freely is fundamentally different. Space-time itself is flowing inward, sweeping everything with it. A vivid analogy comes to mind. Imagine space as a great river rushing into a waterfall. We are like a small boat caught in that river. At the event horizon, the river's flow was so fast that not even light could swim upstream against it. Now, deeper in, the river grows even swifter, roaring ever faster towards some inevitable plunge. We are being carried by this flow of space-time. The idea of escaping back up the waterfall becomes unthinkable. It would require travelling faster than light, an impossibility. So we ride the current deeper. In this river of gravity, we and everything around us are just driftwood swept in by this cosmic current. Space itself is falling inward, dragging us with it at an accelerating pace. The closer we get to the centre, the steeper and more furious this rush of space becomes. As we continue inward, the uneven pull on different parts of us intensifies. That slight tug of war we first noticed grows into a powerful force, stretching us lengthwise. If we were feet first falling, our feet feel a stronger downward pull than our head. If head first, then our head is more strongly tugged. Either way, one end of us is nearer the source of gravity and experiences a greater force. This difference in pull is what physicists call tidal force. We've felt gentle tides in our everyday world. The moon's gravity raises tides in Earth's oceans by pulling a bit more on the side of Earth facing it than on the far side. Here, the tidal forces are not gentle at all. They are overwhelming and increasing rapidly. The black hole's gravity is now so intense and changing so quickly over small distances that it begins to stretch us apart. Our hypothetical spacecraft groans under the stress. Metal frame and supports start to creak. If we imagine being unshielded, our body would begin to elongate subtly at first. A strange sensation, as if an invisible hand were pulling us from our toes. With each mile we fall closer to the core, that hand pulls harder. We are being drawn into a thinner, longer shape. It's not a sensation we can easily compare to normal life. It's as if gravity itself has taken hold of every cell, every atom, and is tugging them in a line. At the same time, we realize something else. While we're being stretched in the vertical direction, we're also being squeezed in the horizontal directions. The same tidal forces that stretch us out also compress our width. They draw matter in from the sides, even as they elongate it. Imagine a lump of dough being rolled into a long strand. It thins and lengthens. We are that lump of dough now, being stretched into spaghetti. Indeed, astronomers have a rather playful term for this deadly process: spaghettification. It was popularized by physicist Stephen Hawking, who described how an unlucky astronaut would be stretched out like a piece of spaghetti by a black hole's gravity. Now, in our journey, we can understand why he chose that analogy. We are experiencing the beginnings of spaghettification. The further we descend, the more pronounced the effect becomes. If we dropped any object alongside us, say a camera or an instrument, we'd see it start to deform as well, drawn out into a long, thin shape. No material or object is immune. Steel, plastic, flesh, bone, it all would stretch under these relentless tides. And unlike the gentle tides of Earth's oceans, here the stretching only increases until the object is unrecognizable. For now, if we assume our craft has some incredible structural integrity, or if we take a more ethereal perspective, we continue our fall, bearing witness to these extreme effects. The view around us remains mostly darkness, but even darkness has been twisted. Perhaps there are still occasional bits of light, maybe the afterglow of shredded matter emitting flashes of energy as it too falls in. And even those might appear as streaks drawn out in the direction of the fall. Everything is drawn toward one point at the center. Space itself feels narrower in that direction. Like all lines converge ahead of us, we might sense that all paths from any direction are pointing toward the same ultimate destination below. The geometry of our surroundings is not Euclidean any longer. It's as if the rules of space have been bent so much that what was once straight now curves inexorably inward. If this black hole were rotating rapidly, we would face yet another twist of fate. A spinning black hole drags space and time around with it, like a whirlpool dragging water. We would find ourselves spiraling as we fall, compelled into orbit by the black hole's rotation, even as we inexorably move inward. This frame-dragging effect would make our path corkscrew toward the singularity. Space itself, twisted by the enormous spin, would further distort our sense of direction. In our journey, we haven't explicitly accounted for rotation, but in reality, many black holes spin, and their rotation adds a swirling pull to everything around them. It's another way black holes bend reality, not just pulling inward, but also twisting sideways, making the plunge even more complex. Time, too, is acting strange, at least when we compare it to the world outside. Inside this gravity well, time passes slower, closer to the black hole than further away. This happens because massive objects, like black holes, create strong gravitational fields that curve and stretch the fabric of space-time. We actually experience a very small amount of time dilation here on Earth because of Earth's gravity. This has been seen on airplanes where clocks tick at slightly faster rates in the air as opposed to on the ground. Astronauts living on the International Space Station also experience time at a slightly different rate because they are further from the gravitational pull of the Earth. To imagine time dilation in action, picture an object traveling towards a black hole. As the object approaches the event horizon, it appears to start moving infinitely slower until the object will appear completely frozen. Yet for all that outside slowness, our personal journey from crossing the horizon to reaching the core will be surprisingly brief. In our frame of reference, this fall might take only a short time, perhaps minutes or less, depending on the black hole's mass, from the moment we pass the event horizon until we meet the center. The irony is profound. To the universe outside, it appears to take forever for us to fall in. But for us, the end comes quickly. Reality itself is warped here, in space and in time, depending on how you look. It's as if the black hole holds us in a timeless grip from the outside, while hurtling us toward our end in very little time from the inside. We fall on, and the stretching intensifies. Now, it is not just a gentle drawing out, but an extreme elongation. Were we to look at a ruler, or any measuring device we brought, we'd find distances in the vertical direction, increasing beyond what they should be, and shrinking in the horizontal. But of course, any rulers we have would themselves be distorted. The very frame of reference we try to use is distorted along with us. This is what it means when we say space-time is curved. Our usual ideas of straight lines, of parallel lines remaining the same distance apart, of time ticking uniformly everywhere, those ideas no longer hold true here. We can imagine shining a laser beam inside this abyss. If we shoot it forward, meaning inward toward the singularity, it will rush ahead of us, but inevitably be consumed at the central point. If we aim it backward, toward the event horizon behind us, we have already learned that it cannot escape. It will just spiral inward, perhaps slower than us, but still doomed. What if we aim it sideways? Outside a black hole, pointing a laser sideways would result in a straight line, or perhaps a curve, if gravity bends it. Here, even a sideways beam curves inward. There is no truly sideways path anymore. Every direction in space eventually tilts toward the center of the black hole. Up, down, sideways. However we move, or whatever direction we send light, all trajectories bend inward now. This is the true meaning of the event horizon's interior. Space is so warped that forward in time carries everything into the central singularity, and there's no detour available. As this realization sinks in, we feel the extreme nature of our predicament physically. The stretching force threatens to tear apart even the atoms that compose us. If our vessel has not already been rent to pieces, it is at the brink. Imagine that earlier analogy of being dough rolled out. Eventually it thins to the breaking point. Or think of a rubber band stretched too far. It snaps. In the case of a black hole's tidal forces, the snap would be catastrophic disintegration. Any object, a spaceship, a human body, a planet, will be pulled into streams of particles. The molecules themselves can be wrenched apart. Even the nuclei of atoms can be ripped asunder by these tidal forces near the final approach. Matter that was once solid becomes a thin ribbon, and then a mere line of subatomic particles spiraling inward. And yet, even these particles cannot avoid their fate. They too must continue to flow down into the central point. In these last stages, physics, as we know it, is reaching a limit. The gravitational field is becoming almost unimaginably large. The curvature of space-time, in other words, the amount space is bending, is skyrocketing. We speak in terms of infinity approaching, densities and forces heading toward limitless values as one nears the very core. Our mind might go numb trying to comprehend it, but we keep describing what we can, as calmly as we can, understanding that words and even thoughts may fail as we edge into the most extreme environment in the universe. Though our journey is taking us toward destruction from a physical standpoint, as narrators and observers, we press on to the threshold of the ultimate unknown. The spaghettification process has stretched and squeezed everything into a narrow pipeline of matter. We find ourselves effectively as part of a column of infalling debris and energy, all channeled toward an infinitesimal point ahead. It's as if the black hole is focusing everything down to one final destination. The reality we knew, of stable shapes, of gentle gravity, of time flowing uniformly, has been left far behind. Here, reality is warped beyond recognition. Through it all, a part of us marvels at the strange beauty of these phenomena. The way gravity can twist and mold the universe is breathtaking, even in its terror. We recall that we are witnessing a process that no human has ever witnessed directly, that existed only in equations and thought experiments. Now it unfolds around us in its full grandeur and menace. In a detached corner of our minds, we find a sense of wonder that manages to coexist with the knowledge of impending doom. It's a reminder that even in the heart of darkness, the laws of nature are majestically at work, doing exactly what they predictably do. Yet it feels almost surreal, like a cosmic ballet of distortion. We sense now that the singularity, the very heart of this black hole, is close. The stretching forces are so strong, the warping of space so complete, that we know we are nearing the end of the line. Just ahead, that final point of infinite density awaits. Before we confront it, we take a moment in this maelstrom to absorb where we are. In these last instants, before the plunge reaches its ultimate conclusion, we have seen space twisted and stretched to its limits. We have felt time altered and slowed. We have observed matter torn apart into strands. We have truly witnessed space-time bent to nearly breaking. Now, with what might be our final thought or measurement, we turn our attention toward the very center, the singularity, the mysterious heart of infinite density that lies just ahead in the darkness. We have arrived at the heart of the black hole's mystery, the singularity. In theory, this is the very center of the black hole, a point, or perhaps a region, where the density becomes infinite and the pull of gravity is immeasurable. Everything that has fallen into the black hole is ultimately brought here, to this final extremity. It defies our intuition utterly. All the mass of a star, or millions of stars in a supermassive black hole, crushed down to an almost infinitely small space. It is a place where the normal rules of physics break down completely. As we drift ever closer to where we believe this singularity resides, we realize we are approaching a boundary, not just in space, but in knowledge itself. What does it look like here? In truth, no one knows for certain. The singularity itself might not look like anything in the conventional sense. There is no light to see, and even if there were, our eyes and instruments would likely fail in the face of such extreme conditions. Perhaps, if we imagine it, it could be a region of blinding brightness or perfect darkness. Both images are equally hard to comprehend. Some theories suggest the singularity is shrouded by something else, perhaps a quantum fuzz or a firewall of high-energy particles, so we may never actually see a distinct point. What we do know is that in the equations of general relativity, everything goes off the scale at this core. Space and time as we understand them come to a halt. Beyond this point, the math yields infinities, and our usual understanding ends. We might attempt to picture it as best we can. Envision all directions of space collapsing into one. Up, down, left, right, all become meaningless, because every direction leads to the same place, the singularity at the center. And time? For anything falling in, time itself comes to an end at the singularity. Just as our traveler cannot avoid moving toward the singularity, any more than we could avoid moving into the future. Once they reach that point, they have no future left. It's as though their personal clock simply stops when it hits this final boundary. This is an unsettling concept, a literal end of time for the falling traveler. The singularity marks the full stop at the end of their story. The conditions here are beyond extreme. The curvature of space-time has become so infinitely steep that it's as if we've reached a wall of reality. The gravitational forces that were stretching and crushing us grow without bound. By now, any object would be torn apart to subatomic pieces, and even those fragments would be contorted and squeezed. The density is unimaginable, trillions upon trillions of times denser than the core of an atom or any material known. We try to find comparisons. A teaspoon of this central core might weigh as much as a mountain, or as an entire planet, or more. In fact, at the true singularity, the concept of weight or mass in a volume loses meaning, because volume itself shrinks towards zero. At this point, we must acknowledge that our journey, physically, cannot continue in any meaningful way. The forces would destroy any probe, any observer, long before reaching this exact center. And even if somehow one could survive, the known laws of physics give no guidance for what happens right at the singularity. It is a mystery in the purest sense. It's not just that we don't have the technology or the means to observe it. Our fundamental theories themselves are incomplete here. General relativity, which so beautifully described the warping of space-time, produces infinities when applied to the singularity. It indicates a breakdown, a place where a new theory is needed. We suspect that quantum mechanics, the laws that govern the very small, must come into play. Perhaps at sizes near the singularity, on the order of the Planck length, incredibly tiny, the fabric of space-time becomes turbulent or foamy. Maybe gravity and quantum physics merge into something we don't yet understand, preventing true infinities from occurring. But without a working theory of quantum gravity, we can only speculate. Speculate. That is all we can do in the face of the singularity. And there have been many speculations. Some scientists have imagined that if one could somehow pass through the singularity, an idea more fantasy than reality given the crushing forces, it might act as a bridge. In the mathematics of spacetime, an Einstein-Rosen bridge, better known as a wormhole, appears in some solutions. In a non-rotating, eternal black hole solution, the equations hint at another universe connected through the black hole's core, effectively a mirror image white hole where matter might spew out. It's a tantalizing idea. Fall into a black hole in one universe and emerge in another, or in a different part of our own universe. Science fiction has often toyed with this notion, but in reality, such a passage seems exceedingly unlikely. The conditions for a stable wormhole are not met in a real black hole that forms from a collapsing star. The tunnel would pinch off almost as soon as it formed, and the tidal forces, as we've seen, would obliterate any traveller long before they could contemplate such an escape route. Yet the idea of the singularity being something other than a dead end is hard to resist. Some theorists suggest that perhaps what we call a singularity is not truly a point of infinite density, but rather something we don't yet understand. A bouncing point, maybe, where the collapse of matter stops and rebounds, potentially seeding the creation of a new universe elsewhere. It's a wild concept, that inside every black hole might lie the beginning of a new universe, a kind of cosmic rebirth hidden within an event horizon. There is no evidence for this, but it shows how, when faced with the enigma of the singularity, our minds reach for creative possibilities. On the other hand, it could indeed be the absolute end. From all we can tell with observational evidence, nothing that falls in ever comes back out. The singularity is the ultimate one-way trap. It swallows matter and energy and hides them behind the event horizon. Whether that matter is forever destroyed or somehow preserved in an unknown form is one of the great unanswered questions of physics. This touches on what scientists call the information paradox, the puzzle of whether information about the things that fell in is lost forever or not. According to quantum physics, information, in principle, shouldn't be destroyed, but a classical black hole seems to erase it completely at the singularity. How this paradox is resolved, we do not yet know. Some believe that perhaps the information is encoded on the event horizon's surface, subtly preserved, or that Hawking radiation, the slow leakage of particles from a black hole, carries away some imprint of it. But deep inside, at the singularity itself, our theories give us no clear answers. Standing here at the brink of the singularity in our thought experiment, we feel the weight of these uncertainties. Our journey has reached a philosophical limit as much as a physical one. We are face to face with the unknown. The singularity is a cosmic sensor. It hides whatever happens in this final crucible from the rest of the universe. No signals can escape to tell the outside world what goes on here. We are alone with the secrets of the black hole's heart, and we cannot share them, even in principle. This aligns with a conjecture in physics often called cosmic censorship, the idea that nature hides singularities behind horizons so they are never naked for us to see. Indeed, every singularity we know of is cloaked by an event horizon, preventing a direct view of these infinities. As our imagined journey draws to this endpoint, it's humbling to realize that we have come as far as physics will take us. We followed the path from the outside universe, across the event horizon, through the warped space-time inside, all the way down to this enigmatic core. And now physics simply shrugs. Here be dragons, as ancient maps would say, at the edge of the known world. We have hit the boundary of knowledge. For our brave traveller, reaching the singularity is the end of the line. Crushed beyond recognition, their physical story concludes here. Their mass, their energy, becomes part of the black hole entirely. There is no tomorrow for them beyond this point. And notably, no outside observer will ever see this moment. To any distant onlooker, our traveller never quite reaches the singularity. In fact, they never even appear to pass the event horizon. The ultimate moments of our journey occur behind an impenetrable veil. From the viewpoint of the universe outside, time has effectively stopped for our astronaut at the edge of the black hole. All the drama of spaghettification and the final plunge into the singularity happens in secrecy, cut off from the rest of space and time. Thus, we confront a profound truth. What lies at the singularity will remain one of nature's deepest secrets, at least until a new understanding or new physics can illuminate it. We are left with only our imagination and the faint whispers of theories to guess at its true nature. Our journey inside the black hole essentially ends here, in silence and enigma. Yet, while we have been consumed by this darkness, we should step back now to the world outside and consider how our fall appears to those who never took the plunge. From afar, our fate looks very different, frozen in time at the event horizon, never to be seen completing the descent. It is to that distant perspective that we now turn, to understand how the black hole guards its secrets from the rest of the universe. Back in the safety of the outside universe, let us imagine a distant observer watching our entire journey from afar. Perhaps a colleague, a friend, or a mission control team is monitoring as we ventured toward the black hole. They have powerful telescopes and instruments trained on the region, hoping to see what becomes of us. From their vantage point, floating light years away under a starry sky, what they witness is very different from what we experienced. As we approach the black hole and eventually cross the event horizon, our distant observers see something eerie. To them, it looks as though we are moving in slow motion, gradually freezing in time at the edge of the black hole's darkness. In the beginning, as we draw near the event horizon, the outside observer notices our spacecraft's movement slowing down. Every maneuver we make, each flicker of our signal, becomes more and more sluggish in appearance. Suppose we were sending out regular pulses, say a bright flash of light every second by our own clock. Initially, those flashes reach the observer 1 second apart. But as we skim closer to the horizon, the interval between flashes, as measured by the observer, starts to stretch. What was once 1 second gaps becomes 2 seconds, then 10 seconds, then minutes, hours, until they effectively cease. Our signals arrive later and later, growing more and more delayed. It's as if a cosmic hand is slowly turning the dial, stretching out our timeline. Not only do our signals slow, they also change in character. Any light we emit begins to shift toward the red end of the spectrum. To the observer's eyes, the bright lights on our ship, perhaps once white or bluish, start to appear dimmer and redder. This is the gravitational redshift at work. The strong gravity at the edge of the black hole drains energy from the light climbing out. A blue beam turns to green, then to red, and then slips into the infrared, where human eyes can no longer see it. If our friend has instruments, They might pick up those infrared rays or radio waves for a time, but even those lengthen into oblivion. Eventually, the light we emit is stretched to such long wavelengths that it's indistinguishable from the background noise of the universe. We fade from visible sight. Imagine our observer watching through an ultra-powerful telescope. They see our ship approaching that dark boundary. Perhaps our ship has some distinctive color or flashing beacon. As the ship nears the event horizon, that color deepens to a dull red and then disappears. The flashing beacon slows until it seems to stop. To the observer, it looks like our spacecraft just hovers at the edge of the black hole, frozen in time, never quite falling in. It's a haunting image, like a ghost caught in a moment, hanging on the precipice of a void. Of course, the reality is that we, the travelers, have already continued past the horizon and met our fate inside. But no information about our ultimate plunge can reach the outside world. From the external perspective, time at the event horizon grinds nearly to a halt. No matter how long the observer waits, they will never see us actually cross the horizon. We get closer and closer, our image dimmer and more red-shifted, asymptotically approaching that boundary, but we never seem to quite vanish through it. In theory, it would take an infinite amount of the observer's time to see us reach the exact point of crossing. In practice, long before that infinite time is anywhere near up, our image will have become too faint to detect. We effectively vanish, not by suddenly dropping out of sight, but by fading away gradually into darkness. Our distant friend might not realize exactly when we passed the point of no return. They might note, it looks like they've almost stopped, as our ship's motions become imperceptibly slow. Over hours, days, years, our signals become so delayed and redshifted that they lose meaning. Eventually, there's nothing at all. No light, no radio whisper, nothing. To the observer, it's as if we've been swallowed by a black shadow that now reveals no trace of us. But notably, they never saw the moment of us being swallowed in any definitive way. We were simply there one moment, approaching that black boundary ever more slowly, and then we became too faint to see. This strange observation is a direct consequence of Einstein's relativity. Time and space are warped near the black hole, and from far away, we perceive that warping as a slowdown of clocks near the gravity well. If our observer had a clock on board our ship in view, say painted on the hull or a digital display, they would have seen it ticking slower and slower. By the end, it might have appeared practically frozen at a particular time. Our frantic fall, which in our perspective took a finite time, looks to the rest of the universe like it's been stretched into eternity. To put it in vivid terms, the event horizon acts like a kind of time trap. Anything that tries to leave slows down and fades. It's as though the black hole is reluctant to let go of even the light from the object it's capturing. The result? A holographic illusion of sorts, where an image of the infalling object remains suspended just outside the horizon. Some scientists often describe it by saying that the information of the object gets smeared on the event horizon's surface, almost like a thin film. Our observer sees only that smeared, delayed remnant. For all practical purposes, the object as they knew it is gone. What does the observer actually see at the black hole now? Without our ship's light, the black hole returns to its inscrutable darkness. Perhaps if there was a bright glowing accretion disk of hot gas around the black hole, as many have, our ship's silhouette might have been briefly visible against that glow, like a dark speck approaching a black sun. But once our light is gone, there is nothing left to mark our presence. The black hole might look just the same as it did before, a dark circular shadow in whatever light surrounds it. Only the fact that the black hole's mass has increased ever so slightly by the addition of our ship's mass would give away that something fell in. And even that increase in mass would likely be undetectable for a small object like a ship. In principle, the gravity field of the black hole adjusts as we become part of it, so an observer far away would eventually feel a slightly stronger pull from the black hole than before, as if the black hole had grown a bit. That is the only real testament to our passing. The black hole becomes just a little more massive, a tiny fraction stronger in gravity. Our distant friend might find this situation bewildering. Imagine calling out over the radio, "We saw you slow down. Are you still there? Did you make it? What's happening?" But there will be no reply. Any signals we try to send from inside the horizon cannot escape to reach them. From their standpoint, it is as if we are eternally silent and suspended at the brink. In time, they come to realize that for all intents and purposes, we are gone. The black hole has taken us, even though their eyes never saw us cross over. If the observer didn't know about relativity, they might even think time had somehow stopped for us, or that we were stuck on the event horizon. But armed with understanding, they know this is just how gravity warps the view. We fell in and met whatever fate awaited us inside. But relativity prevents the outside universe from witnessing those final moments. Nature draws a curtain over the last act of our journey. This frozen-in-time effect has been confirmed indirectly by experiments in less extreme conditions. Atomic clocks placed in strong gravitational fields tick a bit slower than those farther away. We've observed this on Earth by comparing clocks on mountains and in valleys, and with clocks on satellites high above Earth's surface. Around Earth the effect is tiny, but around a black hole it becomes enormous. So enormous that for external observers, time virtually stops at the horizon. There is a poignant thought here. If we, the falling travellers, could somehow look out at our friend while we fall in, impossible once we're inside, but imagine just at the horizon, we would see their time speeding up. The outside universe would seem to race on. In the brief moments before we hit the singularity, we might even witness eons passing in the wider cosmos, in theory. Meanwhile, they see us barely moving. Each perspective is utterly strange to the other. Such is the power of gravity to warp time. Now, let's broaden the picture. Everything that has ever fallen into this black hole, be it gas, dust, planets, stars, or a hypothetical wayward space traveller, will, to an outside observer, be represented by some fading, slowed imprint near the event horizon. Over the eons, a black hole could be thought to carry a kind of record of its meals on that horizon, though in an extremely scrambled and dim form. In practice, we can't actually read this record. The light is gone, and the details are lost to extreme redshift. But conceptually, it's as if the horizon is a theatre curtain, where all the objects that fell in left a final mark as they faded away. For our observer friend, the black hole remains forever a mystery. They cannot see past that curtain of the horizon. All they can confirm is that once we approached close enough, we effectively disappeared from their world. The black hole's reputation holds true. It swallows and doesn't give back. The event horizon behaves like a one-way membrane, letting things in, but nothing out. Over time, our friend will note that the black hole behaves as though it has our ship within it, because of the slight changes in its gravity, or maybe its rotation, if we had angular momentum that got added. But they will never retrieve any message or any evidence of what became of us inside. To learn about our fate, they would have to follow us in, which of course simply traps them as well. It's a cosmic silence that cannot be broken. This is why black holes are often said to have no hair in physics parlance, meaning, from the outside, you can only tell a few simple things about a black hole. Its mass, its spin, maybe its electric charge. It doesn't reveal detailed information about what fell into it. Our observer, looking at the black hole after our disappearance, can at most measure those general properties. The rich story of our journey, our identity, or the composition of our ship, none of that is visible any longer. It has been swallowed by the black hole and locked behind the horizon. And so, to any distant eyes, the black hole appears just as enigmatically dark as ever. In fact, black holes get their name precisely because of this. Even light, travelling at the fastest speed in the universe, gets trapped, making the black hole essentially invisible against the black background of space. Only by contrast with surrounding material or through gravitational effects can we even detect one. In our scenario, once our faint glow died, the observer is left with just a patch of emptiness, detectable perhaps only by the absence of light or by its gravitational pull on nearby stars. In recent times, humanity has actually managed to observe something akin to what our imaginary observer saw. The Event Horizon Telescope project produced the first direct image of a black hole's immediate vicinity, the famous ring of light around the supermassive black hole in galaxy M87. What they saw was a glowing, fuzzy donut of light. That's the hot gas and plasma swirling just outside the event horizon. And in the center of that ring, a dark circle, the shadow of the black hole. That shadow is essentially the region where light is captured, the event horizon and its near surroundings. Everything inside that shadow, including the event horizon itself, is invisible. In that historic image, we effectively saw the outline of where time stands still and nothing escapes. It was a triumph of science and engineering, giving us a visual confirmation of what theory had long predicted. Still, even that image doesn't let us see past the veil. It only shows the silhouette, the border between light and dark. The interior, where we travelled in our thought experiment, remains hidden. Our observer might also be aware of another way we've sensed black holes, through gravitational waves. When black holes merge with each other, they make ripples in space-time that we can now detect with sensitive instruments on Earth. These ripples carry information about the black hole's masses and spins. When scientists first detected them in 2015, announced in 2016, it confirmed not only that black holes exist and collide, it also indirectly reaffirmed that no matter or light escapes during such a merger. The waves were the only sign of that cataclysm. No flashes of light were seen, because the collision happened entirely behind event horizons. Even in these gravitational waves, which come from distortions of space-time itself, the details of what's inside the horizon are absent. They tell us about the mass and spin, again, but nothing of the exotic events at the central singularities, if any. So, for our distant observer, and indeed for all of us who study black holes from afar, we are fundamentally limited. We see the slow-motion disappearance of objects and the aftermath in the black hole's simple properties, but we cannot witness the full story. This is why black holes remain one of the most mysterious phenomena in the universe. We have learned a great deal about them. We can predict how they affect their environment, how they shine when feeding on surrounding matter, how they merge and produce cosmic vibrations. We can even photograph the edge of one. Yet, the internal dynamics, the realm beyond the horizon where we took our imaginative plunge, is sealed off. It's as if the universe has a rule. What happens in a black hole stays in a black hole. The information paradox we mentioned earlier encapsulates our frustration and curiosity about this rule. To the outside, it truly appears that information is lost. Whether it truly is lost, whether the universe might have some subtle way of preserving it, is an ongoing question that scientists are still debating. Our observer can only shrug, unable to discern the truth from their distant perch. However, theoretical hints offer some solace. Stephen Hawking proposed that black holes aren't entirely black. They can emit a very faint glow due to quantum effects, now known as Hawking radiation. Over mind-boggling spans of time, this radiation could allow a black hole to slowly evaporate. If that is true, then perhaps, just perhaps, some information about what fell in might eventually trickle out, encoded in that radiation. But Hawking radiation is incredibly weak for large black holes. Our observer would never notice it in any practical time frame, certainly not during their lifetime, or the lifetime of the universe for that matter, for a big black hole. It's more of a theoretical endgame, billions upon billions of years hence. From the perspective of our friend watching, though, none of that is observable. For all they know, once we faded out, that was the end of our story, accessible to them. They are left staring at a silent, dark sphere, our fate sealed inside, with only theories to speculate on what has become of us. To them, the black hole remains as enigmatic and silent as ever. As our observer turns their eyes away from the black hole, they might reflect on what they have just seen. It defies common sense, an object seemingly freezing in time, then vanishing. If the observer didn't know the science, it would seem like pure science fiction. And yet, this is reality in our relativistic universe. The calm, steady flow of time we experience daily is not absolute. It can be bent and twisted by gravity. Black holes push this flexibility of time to its extreme. In a way, our distant witness has seen a kind of immortality, an image of us that will remain near the event horizon for as long as the universe exists. Beyond a certain point, that image becomes entirely undetectable. It's a ghostly remnant of our presence, stretched across time. We, the actual travellers, have long since met our end inside, but a fading imprint of our approach to the black hole lingers at the edge. This thought is both haunting and fascinating. The idea that every person or object that has fallen into a black hole might still, from the outside view, be there in a suspended state, just too redshifted to see. Layer upon layer of infalling matter, frozen just before the brink. It challenges our usual notions of death and disappearance. In the universe of relativity, ending is not always a sudden vanishing act. Sometimes it is a slow fade, drawn out indefinitely from another's perspective. Finally, our imaginary observer must accept that the journey they hope to follow has gone dark. The black hole remains, as ever, a closed chapter to prying eyes. Perhaps they record the increased mass or note the disappearance of our signals. In the end, they write in their log that we have passed beyond the veil. For us, now melding with the black hole's interior, the adventure reached a conclusion at the singularity. For our friend outside, it's as if the final pages of that adventure were blank, unreadable. This is where the limits of observation meet the vast unknown. In a sense, knowledge itself has an event horizon here. In summary, observing a black hole from a distance teaches a humbling lesson. There are limits to what we can see and know, enforced by the universe's physical laws. We watched our traveller fall in, but could not watch them finish their journey. Time appeared to stand still, and then the scene went dark. the black hole keeps its secrets well. Yet, humans are clever and curious. Even if we cannot directly see beyond the horizon, we continue to devise ways to study black holes indirectly, to test our theories against the hints nature gives us. Each observation, whether it's an image of a black hole's shadow or the detection of gravitational waves from a merger, adds a piece to the puzzle. We inch closer to understanding what might truly happen in those realms we cannot see. Our distant observer might move on, aiming their telescope elsewhere, but the black hole remains an object of deep contemplation. It sits there, seemingly eternal, with all its captured moments frozen at its edge and everything else locked inside. It reminds us of the vast areas of reality we have yet to grasp. It silently challenges us to keep searching for answers. Looking at that dark giant, we are filled with both humility and wonder. It underscores that there are realms where our knowledge falters, boundaries where our exploration meets a wall. And yet, the presence of such mysteries is itself an inspiration. Black holes, in a way, are both boundary and beacon, marking the limits of what we know, while beckoning us to push beyond those limits in our quest to understand the universe. Even though our tale has taken us as far as empirical observation and established physics allow, the quest does not end here. The next steps belong to theory, to imagination, and to future discoveries. Perhaps one day, new physics or novel observations, like those faint Hawking rays or quantum signatures, will give us a peek behind the curtain. Until then, we have to be content with the shadows and echoes that escape a black hole's clutches. For now, the black hole holds its mysteries tight. Time remains frozen at its threshold, guarding the secrets within. And we, observing from a distance, can only watch and wonder. We must continue to explore through thought and ingenuity, hoping to unravel the remaining enigmas of these cosmic maelstroms in the chapters to come. Now we linger at the very edge of an abyss, suspended near the event horizon of a black hole. All our usual certainties begin to dissolve. Space feels distorted and stretched, and time itself, starts to lose its steady rhythm. A minute no longer seems like a minute. Each second draws out longer and longer, as if hesitant to pass. In this strange realm of gravity, seconds can feel like an eternity. We are witnessing one of the universe's most astonishing tricks, the dilation of time under the spell of a black hole. From a safe distance, an outside observer would see our every movement slowing down. If someone far away watches us drift close to the black hole's boundary, they would notice our motions becoming sluggish, then almost imperceptible. To them, it would appear as though we are moving through thick, invisible syrup. With each passing moment, our progress seems to slow further. Eventually, as we reach the very threshold of the black hole's darkness, we could appear completely frozen. We would hang there at the edge of night, as if caught in a timeless tableau. To you, inside the spacecraft approaching the black hole, nothing seems strange about your own flow of time. Your heart still beats steadily in your chest. You breathe in and out, and your clock ticks along normally from your perspective. But when you look outward to the universe beyond, it's as if someone pressed fast forward on reality. The stars far from the black hole speed through their life cycles in a blur. Distant galaxies whirl and evolve at breakneck pace. In what feels like mere moments to you, you might witness years or centuries pass in the wider cosmos. It is a surreal, almost mystical sight, as though you've been granted a window into the future. seeing time outside race ahead while your own time crawls. For your friend watching from afar, the situation is reversed. They see you moving in slow motion, each gesture taking ages. Eventually, as you reach the threshold of the black hole's darkness, you would appear almost frozen at the edge, a ghostly image growing dimmer and redder as the light from you struggles to climb out of the intense gravity. In fact, to that distant observer, you would never be seen to completely disappear. This phenomenon is gravitational time dilation taken to an extreme. We experience a tiny bit of it here on Earth. Clocks at sea level tick a smidgen slower than clocks on a mountaintop, because sea level is deeper in Earth's gravity. The effect is minuscule in everyday life, but around a black hole it becomes colossal. Close to the black hole's maw, time itself is stretched and slowed in a dramatic fashion. Seconds for you near the horizon might correspond to hours, days, or more for someone far away. Imagine holding a clock in your hand as you venture near the black hole, while a friend remains safely distant with an identical clock. At first, both clocks tick almost together, second by second. But as you descend deeper into the gravity well, you would see your friend's clock, from your viewpoint, start to tick faster and faster. Or rather, your own clock is the one slowing relative to theirs. If you tried to radio a message out, your words would elongate and deepen, growing farther apart in time. The outside universe's replies would speed up, sounding high and hurried, as if the cosmos were impatiently fast-forwarding. It would feel uncanny. Time has become unhinged from its usual uniform pace, differing from one location to another. Now imagine you decide to retreat, to pull away from the black hole after spending what you felt was a short while near its edge. You fire your thrusters and slowly climb out of the gravity well. As the black hole's grip on you weakens, your clock's pace aligns more and more with the rest of the universe. But when you finally return to open space and compare notes, you make a heartbreaking discovery. Far more time has passed in the outside world than passed for you. Perhaps you only experienced a few hours near the horizon, but outside, years have slipped by unnoticed. You might find that the stars have aged, that people you knew have grown older or moved on, all while you merely circled in the black hole's vicinity. In effect, you have travelled into the future. The black hole's gravity acted like a one-way time machine, propelling you forward relative to everyone else. Such gravitational time travel doesn't violate any law of physics. It is a natural consequence of gravity's warping of space-time. Yet it feels almost supernatural. Science fiction stories have imagined scenarios like this. Astronauts who venture close to a black hole and return home to find decades or centuries have passed, their loved ones gone or changed beyond recognition. Indeed, science fiction has depicted explorers near a black hole coming back to find their world far in the future, a dramatic but physically plausible outcome. Though poignant and strange, it underscores how profoundly a black hole can separate one observer from another's flow of time. Back near the black hole's event horizon, time's behavior leads us to deeper puzzles. If, from the outside, we can never quite see an object actually cross the horizon, if it appears frozen forever at the edge, what does that mean for the fate of something falling in? Consider a traveller, or a piece of matter heading inward. To an external observer, it slows and fades, never quite vanishing. It's as though the black hole wears a frozen mask of everything it has captured. In a poetic sense, the surface of the black hole might be thought to hold a fading imprint of each object that fell in, suspended just outside the point of no return. This notion hints at mysteries we don't yet fully understand. Of course, in the infalling object's own frame of reference, nothing peculiar happens at the horizon. It crosses over in a finite amount of time and continues inward. But the fact that we, watching from afar, never see it truly disappear suggests something almost magical. The information of that object, the record of its existence, might never be lost to the outside universe, at least not until unimaginable eons have passed. This conundrum is one part of the story that remains unsolved and will invite us deeper into the black hole's secrets later in our journey. Standing here, just outside that shimmering boundary, we feel the unsettling effects of extreme gravity. We can still choose to turn back, to return to safer space. But one step farther, one gentle nudge, and we would cross the horizon where choices run out and time takes on a one-way march inward. It is truly a horizon in time, as much as space. Beyond it, all paths lead down to the unknowable singularity. No wonder it's often called the point of no return. In these moments, holding position near this boundary, we sense a profound stillness. Every heartbeat is drawn out. Every second feels precious and heavy. It's as if the universe is quietly urging us to pause and reflect when we stand in the presence of such a gravitational titan. The normal rules have blurred. Up feels down, seconds feel like eternity, and our intuition falters. We're reminded that black holes warp not just space, but our very sense of reality. What other marvels might such an object hide? If gravity can stretch time to near infinity, could it also twist space into bizarre shapes? Our experience so far has been at the threshold. Time dilated, space curved around the black hole like a distorted mirror. Beyond slowing time, might a black hole also serve as a bridge to entirely different regions of space, or even other universes? The questions beckon us forward. Our minds turn to the tantalizing idea of wormholes, hypothetical tunnels through space-time that might connect distant points. Time has been stretched nearly to breaking. Now we wonder if space can be bent until it folds over on itself, opening a path to elsewhere. We turn our attention to the idea of wormholes, theoretical bridges that could link one corner of the universe to another. The notion sounds like pure fantasy, yet it arises naturally from Einstein's equations if one contemplates extremely warped space-time. A wormhole is imagined as a shortcut, a tunnel that a traveller might enter in one location and emerge from in a completely different place or time. It is a mind-bending concept, a pathway through the fabric of reality itself. Imagine the fabric of space as a vast sheet, with 2 points on that sheet that are far apart. Ordinarily, travelling between them means crossing the expanse of the sheet, a long journey. But if you fold the sheet so that those 2 points touch, then punch a hole through the layers, you've created a shortcut. That is essentially the wormhole idea. You enter the tunnel at one mouth, and almost instantaneously exit at the other mouth somewhere else, perhaps millions of light years away, or in a different era altogether. It is as if distance becomes irrelevant, bypassed by a secret hallway through the higher dimensions. This idea first emerged not in fiction, but in scientific contemplation. In the 1930s, Albert Einstein and Nathan Rosen considered whether the equations of general relativity might allow such bridges. They described what came to be known as an Einstein-Rosen bridge, essentially a wormhole connecting two regions of space-time. On paper, it appeared that if a black hole could be connected to a mirror image exit, sometimes imagined as a white hole, it would create a tunnel. In theory, one could fall into such a black hole and not face ultimate destruction, but rather pop out in a different region of the universe. It was an intriguing solution to the equations, hinting that a black hole might not be a one-way dead end after all. It was soon realized, however, that these early wormholes came with a significant catch. They were not traversable in practice. The Einstein-Rosen bridge solution seem to pinch off too quickly for anything or anyone to get through. If you tried to pass into such a wormhole, it would collapse before you could emerge on the other side. It was like a door that slams shut the instant you crack it open. For any traveller, it was effectively an impassable barrier, a tunnel that closes faster than light could travel through it. Still, the possibility tantalized physicists and writers alike, and over the decades they continued to explore what wormholes might be and under what conditions, if any, one could journey through them. For a wormhole to be truly traversable, to allow passage from one end to the other, it appears something extraordinary is needed to keep its throat open. By default, gravity pulls the wormhole closed. But if one could line the tunnel with an exotic form of matter that has negative energy or pressure, it might act like an anti-gravity brace, holding the passage open. This exotic matter has never been observed in bulk, though quantum theory hints it can exist in small amounts, for instance, in the Casimir effect between closely spaced metal plates. Such material would be the magic ingredient to stabilize a wormhole long enough for travel. You might imagine it like a translucent scaffold or pillar of light propping open a tunnel that would otherwise collapse. Without it, any wormhole would snap shut the instant it formed, if it formed at all. And so the dream of walking through a shortcut in space-time hinges on physics we have yet to discover or control. Physicists like Kip Thorne have even outlined how a traversable wormhole might be possible if one could thread its throat with something having negative energy density, this very exotic matter. While negative energy does exist in quantum physics, no one knows how to accumulate enough of it to stabilize a macroscopic wormhole. Stephen Hawking speculated about a chronology protection conjecture, essentially the idea that the laws of physics might prevent wormholes from allowing time travel and creating paradoxes. Many suspect that even if wormholes can form, nature would enforce cosmic rules that forbid using them to rewrite history. As speculative as all this is, it hasn't stopped our imaginations. Wormholes feature prominently in science fiction stories, serving as cosmic subways for adventurers or gateways to other times. In those tales, travelers step through shimmering portals and emerge in distant galaxies or even parallel universes. While fiction takes liberties, often depicting wormholes as stable, well-behaved tunnels with swirling light shows, the truth is, we have no evidence that nature provides them at all. They remain mathematical solutions and playful thought experiments at this point, not a confirmed part of our universe's repertoire. Consider what a journey through a wormhole might feel like, if it were possible. As you approach the mouth of the tunnel, from the outside it might resemble a black hole, a dark sphere with intense gravity. But instead of ending in a crushing singularity, the interior space bends around and reconnects elsewhere. Crossing that threshold, you might see the universe behind you warping strangely, shrinking as if in a funhouse mirror, while ahead, a pinprick of light marks the exit. The passage could be instantaneous, or time itself might get scrambled in transit. You could emerge to find hardly any time has passed at all for you, even though ages went by outside, or vice versa. In one scenario, you might enter a wormhole, travel across the galaxy in seconds, and find you've arrived not only in a far distant place, but perhaps in a different epoch of time. Maybe the far future, or deep past, relative to when you entered. Now imagine stepping through such a portal, and finding yourself not only in a different place, but perhaps in a completely different galaxy. In an eye blink, the familiar star patterns of our night sky would be gone, replaced by strange constellations swirling around unknown suns. The experience would be both exhilarating and eerie. One moment you're near our sun, and the next you've stepped out under alien skies thousands of light years away. It would be the ultimate voyage, walking through a door and arriving where no rocket could ever carry you within a human lifetime. The thought of it fills the mind with wonder and trepidation. The very idea of using wormholes for time travel arises from their strange geometry. If one mouth of a wormhole were moved at high speeds or placed in a different gravitational field than the other, the two ends could age at different rates, thanks to time dilation. Then traveling through the wormhole would be akin to stepping into a different time as well as place. This leads to the all-too-familiar paradoxes. What if you emerged in the past and could meet your earlier self? Could you alter events and create inconsistencies in history? These questions venture into the philosophical and have made physicists cautious. Most suspect that some yet unknown mechanism would prevent such causality violations. It might be that wormholes simply cannot be used as time machines, preserving the consistency of history, Hawking's chronology protection in action. Still, it's thrilling that general relativity even allows us to pose these questions. Wormholes illustrate just how mind-bendingly flexible space-time can be in theory, even if reality seems to keep such wild possibilities out of reach. Returning to reality, we must admit that so far we have zero empirical evidence for any kind of wormhole. Astronomers have discovered many black holes by their effects on nearby matter and light, but no wormhole has announced its presence. If wormholes exist naturally, they might require conditions the universe rarely or never provides, or they might be hidden in the quantum foam of space-time, appearing and vanishing on scales far too small to traverse. Some theories even suggest that microscopic wormholes could pop in and out of existence in the subatomic realm, but nothing could pass through them, except maybe a bit of quantum information. For now, wormholes remain mathematical curiosities and speculative fiction. Nevertheless, the wormhole concept continues to captivate scientists and the public alike. We dream of interstellar travel that sidesteps the light speed limit, and wormholes tantalizingly suggest it might be possible, at least in principle. Imagine a future civilization discovering or manufacturing a stable wormhole. The far edges of the universe would suddenly be within reach. An explorer could step through a door on Earth and emerge near a star in another galaxy, as casually as stepping into another room. Distances that would take millions of years to cross by spaceship could be bridged in an instant. The human desire to explore finds a hopeful echo in the wormhole idea, suggesting that perhaps the vastness of space might not remain an insurmountable barrier forever. Some researchers have speculated about how wormholes might form or be harnessed. Could the early universe have spawned wormholes that still survive? Could an advanced civilization hold open a small quantum wormhole and enlarge it, threading it with negative energy? These possibilities remain in the realm of pure speculation. Every known process in the universe, from collapsing stars to high-energy collisions, yields black holes or other well-understood objects, never a visible wormhole. If wormholes are out there, they're either extremely rare, fleeting, or well hidden. Interestingly, researchers have even devised clever laboratory experiments to mimic certain aspects of black holes and possibly wormholes. Using flowing water, fiber optic cables, and other media, they create analogues of event horizons to test Hawking's ideas and related phenomena. In one setup, a shallow water channel creates a region where surface waves cannot escape, mimicking a horizon, and tiny ripples, analogous to Hawking radiation, have been detected. In another, laser light in a fiber has simulated a horizon and produced faint signals akin to what a quantum prediction would expect. While these laboratory analogues don't prove that real black holes or wormholes behave the same way, they offer intriguing hints and boost our confidence that the mathematics is not misleading us entirely. Having pondered these hypothetical bridges through space-time, we naturally start to wonder about what might lie at the other end of such a tunnel. If one mouth of a wormhole could be a black hole, what would the other end be? Could it be another black hole elsewhere? Or might it be something entirely different? Perhaps the opposite of a black hole. This line of thinking draws us to another extraordinary concept: the white hole. If black holes are cosmic drains, forever pulling things in, then white holes are envisioned as cosmic fountains, objects that only spit things out and refuse to let anything in. They are, in theory, the mirror image of a black hole, an idea as puzzling as it is captivating. Our journey into the Maelstrom's mysteries now leads us to consider these theoretical twins of black holes and the secrets they might hold. Picture, for a moment, a black hole running in reverse. Instead of a dark maw pulling everything inexorably inward, imagine an orb in space that only ever pushes things away. This is the essence of a white hole, a hypothetical cosmic object that functions as the mirror image of a black hole. Just as nothing can escape a black hole once past its event horizon, nothing can enter a white hole beyond its own event horizon. It's a strange idea, an anti-black hole, where all paths lead out and none lead in. If you were watching from a safe distance, a white hole might initially look exactly like a black hole. It could have mass, it could bend light and tug on nearby objects with intense gravity. In those ways, it would seem the same. There might even be a swirling disk of gas and dust orbiting it, just as we see around feeding black holes. But there would be a crucial difference. In a white hole's case, that matter isn't swirling inwards. Anything that strays too close to a white hole would be violently flung outward. The white hole's event horizon is a boundary of no admission rather than no escape. To an observer, everything about its appearance might scream black hole, until suddenly it does something no black hole ever does. It belches out a burst of matter or energy, an outward explosion with no obvious cause. In that moment, you'd know this is no black hole at all, but its long-rumoured opposite. Physicists define a white hole as a black hole's time reverse. In the mathematics of general relativity, if you take the solution that describes a black hole and imagine running time backward, you get a white hole solution. In a black hole, things fall inexorably to a central singularity. In a white hole solution, things emerge from a central singularity and fly outward. Where a black hole's interior singularity is like an ultimate future endpoint for anything that falls in, where timelines end, a white hole's singularity would be an origin point, where timelines begin. It's like watching a film of a black hole devouring a star, but run in reverse. You'd see debris flying outward and somehow coalescing back into an intact star, which then floats away. Such a sequence is impossible in normal experience, yet as a time-reversed scenario of general relativity's equations, it is perfectly valid. This whimsical reversed movie encapsulates the essence of a white hole, the undoing of a black hole's deeds. This idea leads to some astonishing implications. If a white hole existed, the interior of that region would be completely sealed off from any events in the outside universe prior to its formation. No outside occurrence could ever influence what's inside a white hole, just as no external force can reach into a black hole's interior. However, the interior of a white hole could still affect the outside, since it can throw matter and light outward across its horizon. In effect, a white hole could inject new material or energy into the universe, but nothing could disturb it from outside. It would be an isolated bubble of space-time that can only give, never take. In a sense, a white hole could be thought of as the universe's way of giving something back, expelling matter and energy, rather than forever swallowing it. But where would that outflowing matter and energy come from? In theory, it comes from whatever fell into a corresponding black hole, if we imagine the two are connected by a wormhole. It's as though a black hole takes in material, funnels it through a hidden conduit, and a white hole spurts it out in another place or time. Some have even speculated that every black hole could be paired with a white hole in another universe. What disappears into a black hole in our cosmos might burst out of a white hole somewhere else. In that scenario, a white hole would serve as the big bang of a new universe, receiving all the mass a black hole gobbled up and expelling it anew. This idea is extremely speculative, far beyond any evidence we possess. Yet it has a poetic symmetry. A black hole represents an ending in one place, while a white hole represents a beginning in another. However, the reason we speak of white holes only in hypothetical terms is because, so far as anyone can tell, they do not exist in our universe, or at least, none have been found. Why might that be? The arrow of time in our universe points one way, from past to future, with ever-increasing entropy, disorder. A white hole, by its nature, would seemingly violate this principle. Imagine reversing the flow of time, smoke returning to a chimney, broken cups reassembling on a table. That's the kind of reverse logic a white hole implies. It would be a region where time runs opposite to normal, where effects precede causes if described in everyday terms. Our universe strongly favors forward-in-time processes. Stars shine by converting fuel and producing heat. Eggs break and scramble, but never spontaneously unscramble themselves. A white hole would be like an egg, magically reforming and jumping back into its shell. Not forbidden by mathematics, perhaps, but so fantastically unlikely that it never happens in nature. To exist at all, a white hole would likely require extraordinarily special conditions, the kind that don't arise in our universe. Or if they did, they'd be fleeting. Some theorists argue that even if a white hole could form, it would be unstable. The moment any stray piece of matter or a random particle from the outside universe touched the white hole's horizon, the solution might break down and convert into a normal black hole. In other words, a white hole might instantly self-destruct if disturbed, collapsing into the very thing it is the reverse of. This inherent instability is a big reason many physicists doubt white holes are physically realized. They are like a perfectly balanced house of cards, possible in theory, but the slightest breeze will collapse them into a more mundane configuration, in this case, a black hole or just dispersed energy. Nonetheless, the concept of white holes continues to fascinate as a thought experiment. It forces us to confront how time and physics operate under reversed conditions. It teases us with the idea of a place where time's arrow flips, a region of space-time that remembers nothing of the universe's past, but can influence its future. The very notion is a profound reminder of how symmetric the equations of physics can be. They permit solutions that look like our familiar world run backward. White holes make us ponder whether the one-way flow of time we experience is a fundamental law, or just a quirk of initial conditions. They show us that, in theory, the universe could have been very different, a place where outflows happen without inflows, where light can only escape and never enter. Despite our lack of evidence, a few scientists have dared to speculate about possible indirect signs of white holes. For instance, could certain unexplained cosmic phenomena, like brief, intense bursts of radiation, be the result of a white hole momentarily sprouting into being? One idea suggested that perhaps a small primordial black hole, at the end of its life, could transition into a white hole and expel its remaining contents in one final burst. Some even wondered if mysterious fast radio bursts or high-energy gamma flashes might be cries of these theoretical events. So far, observations have not borne this out. All such bursts have more mundane explanations, and no distinctive white hole signature has been recognized. But the fact that white holes inspire these creative hypotheses shows how they spark our imagination about what might be lurking in the shadows of our understanding. Our searches have turned up nothing that we can confidently label a white hole. Every energetic event observed, supernova explosions, gamma-ray bursts, active galactic nuclei, has a conventional explanation involving known physics: a star collapsing, neutron stars colliding, matter accreting into a black hole. We haven't found any miraculous outpourings that defy those explanations. In general, it seems our universe simply doesn't make white holes, at least not in any abundance or in forms we can detect. Maybe the universe's choice of a one-way time direction, from a highly ordered Big Bang to an ever more disordered future, means that only black holes get realized, and their time-reversed twins are ruled out. Perhaps white holes are confined to the mathematical realm, existing as a curious possibility that our universe, with its asymmetry in time, doesn't permit. That being said, some modern theoretical work has given white holes a surprising relevance in our quest to understand black holes themselves. The renowned physicist Carlo Rovelli and his colleagues, working in a framework called loop quantum gravity, have proposed that what we call the singularity inside a black hole might not be the end of the story. Instead, as a black hole evaporates and shrinks to a very small size, quantum effects could cause the collapse to rebound, essentially turning the black hole into a white hole at the very end of its life. According to their calculations, instead of a singularity, there's a bounce when the density becomes extreme, and the black hole explodes outward as a white hole, releasing everything it had consumed. In this picture, information isn't lost at all. It's trapped for a long time inside the black hole, and then one day, far, far into the future, it bursts back out in the final white hole explosion. It's a radical idea, providing one possible resolution to the information paradox. Importantly, it suggests that black holes aren't the ultimate destructive endpoints, but could be transformations, from collapse to expansion, like cosmic phoenixes. Imagine such a scenario. A black hole, after trillions upon trillions of years of slow evaporation, has dwindled to a tiny size. Suddenly, quantum forces trigger a violent bounce. The black hole's dark interior reverses into a brilliant outpouring. In a final, short-lived blaze, a white hole erupts where the black hole once stood, spewing out all the remaining energy and information. The darkness becomes light. The hidden secrets are released. Then, after this brief outburst, the white hole fades away, leaving emptiness behind. This dramatic finale, if it truly occurs, would be nearly impossible to witness given the unimaginable timescales involved. The last black holes in the universe would die long, long after the last stars have gone cold, perhaps 100 years from now or more. Still, it's captivating to think that the ultimate end of a black hole might not be quiet disappearance, but a grand, if lonely, fireworks show in the darkness of a very distant future. Even if such black hole to white hole transitions do happen, the white hole stage would be extremely brief, astronomically speaking, and likely at microscopic scales. By the time a black hole is ready to burst, it would be tiny, perhaps with the mass of a mountain or much less. The final white hole event might release a pulse of particles and radiation and then cease. Detecting something like that in our current universe borders on hopeless. But the theory at least offers a logical thread connecting black hole death to a kind of rebirth. It's a beautiful example of how thinking about white holes, these neglected twins, can feed back into our understanding of the more familiar black holes. As we reflect on these gravitational mirror twins, we find ourselves filled with wonder at how else the cosmos might have been. White holes, whether they truly exist or not, push us to think beyond the bounds of ordinary experience, into realms where time and space dance to a very different tune. They remain hypothetical, but even as thought experiments, they enrich our understanding of what the laws of physics allow. Through contemplating white holes, we gain a deeper appreciation for the mysterious extremes that nature might hide. From this reflection, another facet of the black hole mystery emerges, one that lies at the smallest scales of reality. To truly unravel what happens in and around black holes, we must venture into the realm of the quantum. It is at the intersection of gravity and quantum mechanics that some of the deepest puzzles appear. And so, our journey now turns to this subatomic frontier, a realm of subtle whispers and quantum echoes, where particles flicker at the edge of the abyss, and even information itself faces a paradox. At the very edge of a black hole's darkness, where gravity is supreme, but quantum rules cannot be ignored, something remarkable occurs. What we think of as empty space is not truly empty. It seethes with tiny, fleeting particles. According to quantum physics, the vacuum is alive with virtual particle-antiparticle pairs that constantly form and annihilate each other, disappearing almost as soon as they appear. Under normal circumstances, this phantom dance goes on unnoticed, a quiet background hum of the quantum world. But near a black hole's event horizon, this subatomic jitter takes on profound significance. Picture one of these ephemeral particle pairs popping into existence right at the black hole's boundary. Ordinarily, the pair would annihilate each other in a flash, returning their borrowed energy to the vacuum. But here, the gravity is extreme. It can snatch one particle of the pair and pull it across the event horizon, while the other manages to escape into open space. Separated like this, the two particles cannot destroy each other. The one that escapes becomes a real particle, carrying away energy that it essentially steals from the black hole's gravitational field. The unfortunate partner, dragged inside, carries negative energy from the outside perspective into the black hole. The result is subtle but astonishing. The black hole loses a tiny bit of its mass energy, and a new particle is emitted away into the universe. To an outside observer, far from the black hole, it would appear that the black hole is not completely black after all. Instead, it seems to glow faintly, emitting a trickle of particles and radiation. This phenomenon, predicted by Stephen Hawking in the 1970s, is known as Hawking radiation. The bigger and more massive the black hole, the weaker this glow, which is why we haven't observed it from astrophysical black holes. They are too cold and dim in this sense. But in principle, a black hole behaves like a very cold object, radiating slowly into space. It's as if the black hole has a very low temperature warmth, a whisper of heat leaking out from just beyond the event horizon. This revelation was shocking when Hawking first derived it. It means black holes are not eternal. Left alone, a black hole will very slowly evaporate over time, radiating away its mass. The timescales are enormous. For a black hole the mass of the Sun, it would take about 10⁻�67 years to evaporate completely, far longer than the current age of the universe. Larger black holes last even longer, while tiny black holes would evaporate much faster. Nevertheless, the conclusion is inescapable. Given enough time, black holes will fade away, eventually disappearing in a final burst of Hawking radiation. It's a strange image. A great black hole, after eons of darkness, quietly fading like a dying ember. But Hawking's insight raised an even deeper puzzle, the problem of information. When the black hole evaporates entirely, What happens to all the information of the objects that fell into it? According to quantum physics, information about a system's initial state cannot be destroyed. It may be scrambled or transformed, but it's fundamentally preserved. Burn a book, and you get ash and smoke. In principle, if you had all the smoke and ash and an infinitely precise understanding of physics, you could reconstruct what was in the book. Quantum mechanics holds this principle sacred. Information is never truly lost, only changed in form. Black holes seem to challenge this principle in a frightening way. When something falls into a black hole, from the outside perspective, it's gone, lost beyond the horizon. If the black hole then evaporates completely, emitting what appears to be just featureless Hawking radiation, it's as if the information about what fell in has vanished from the universe. The Hawking radiation, as Hawking originally calculated it, carries no imprint of the infalling objects. It is almost perfectly random, determined only by the black hole's mass, spin, and charge. This scenario suggested that information might be destroyed, a violation of quantum law. This conundrum is known as the black hole information paradox. For a long time, Stephen Hawking himself argued that the information truly is lost behind the horizon, and he was willing to accept that quantum mechanics might allow this exception. He even made a famous bet, insisting that black holes destroy information. On the other side, physicists like Leonard Susskind and John Preskill vehemently disagreed, arguing that somehow, in some deeply hidden way, the information must be preserved. This debate raged for decades, the so-called black hole war, and it drove significant advances in theoretical physics as each side tried to outwit the other with thought experiments and calculations. One resolution that emerged from these battles was a radical rethinking of the black hole's nature. Rather than being an ultimate information grave, a black hole might be an incredibly efficient information storage device. In the 1970s, physicist Jacob Bekenstein had already proposed that black holes have entropy, a measure of information content, proportional to the area of their event horizon. It was a shocking idea, suggesting that all the information of whatever falls in is somehow encoded on the horizon's surface. Later, in the 1990s, Susskind and others broadened this into the holographic principle. The holographic principle posits that all the information within a volume of space can be described by information on the boundary of that space. In the case of a black hole, it suggests the three-dimensional contents of the hole are stored on its two-dimensional event horizon, like a cosmic hologram. This concept implies that a black hole's interior is effectively encoded on its surface, a truly mind-bending idea. Yet this astonishing notion is exactly what the mathematics of gravity and quantum theory seem to suggest. If the holographic principle is correct, it offers a way that information might escape a black hole, not in any recognizable form, but encoded in the Hawking radiation in a highly scrambled way. Rather than being truly random, the radiation would carry subtle quantum correlations imprinted by the objects that fell in. To an ordinary observer, these correlations would be practically indecipherable, much like trying to read smoke trails to divine the contents of a burned book. But in principle, the information is there. With a perfect understanding of quantum gravity, one could imagine decoding those faint quantum echoes of information hidden in the radiation. Thus, nothing truly vanishes behind the horizon. It's preserved, but in a form so encrypted that for all practical purposes, it's lost to any observer without godlike insight. The idea that a black hole's surface holds its information, and that this info slowly leaks out over time, has gained considerable favour. In fact, Stephen Hawking eventually conceded that information is likely preserved. In 2004, he retracted his original claim and paid off his bet. acknowledging that the emerging consensus, largely thanks to holographic ideas, was that black hole evaporation does not destroy information. However, exactly how the information gets out, by what mechanism those correlations encode the detailed story of everything that fell in, remained an unsettled question. Hawking's capitulation was a triumph for quantum mechanics, but it left much to be understood in detail. One powerful line of evidence supporting the information is preserved view comes from string theory. In a breakthrough known as the ADS-CFT correspondence, physicists discovered a mathematical equivalence between a gravity-filled world with black holes and a quantum system without gravity on its boundary. In this dual picture, anything that happens to a black hole is completely mirrored by processes in a lower dimensional quantum system that has no gravity, and that system manifestly preserves information. This holographic duality, often called gauge-gravity duality, offers strong reassurance that information doesn't vanish. Whatever a black hole swallows is fully encoded in subtle quantum states on its surface or beyond, and in principle can be recovered, though in practice it might be insanely hard to decode. Such theoretical insights give hope that our framework is consistent. Black holes do not defy quantum law, even if we are still working out the details of how the information gets out. This is where the cutting edge of physics continues to probe. Some researchers now propose that black holes are not truly bald at all, but possess what they whimsically term quantum hair. Faint imprints of the stuff that fell in, left behind in the black hole's gravitational and quantum fields. Such quantum hair would mean no two black holes are exactly identical unless they've consumed exactly the same things. It would offer a mechanism for information to be reflected in the outgoing Hawking radiation, however subtly. If this is true, it might resolve the information paradox by ensuring that Hawking radiation is ever so slightly different depending on a black hole's history, carrying away the hidden information after all. It's a compelling proposal, though proving it experimentally is extremely difficult. For now, quantum hair remains a fascinating idea, awaiting further theoretical and observational development. This hypothesis will continue to be explored as our understanding of quantum gravity grows. Experimental evidence for these ideas is extremely hard to come by. Black holes, especially large ones, radiate so feebly that detecting Hawking radiation from afar is essentially impossible with current technology. Even without direct observations, these inquiries keep the questions alive and guide theoretical progress. Still, physicists press on with thought experiments and clever analog models to test their theories bit by bit. Interestingly, researchers have even created laboratory experiments to mimic aspects of black holes and their Hawking radiation, using fluids, optical fibers, and other platforms. They've made analog event horizons to see if a form of Hawking radiation can be observed. In one notable case, a team used a row of flowing water to simulate a horizon for surface waves, and they observed tiny ripple patterns consistent with Hawking's predictions. In another, laser pulses in a fiber optic cable produced a horizon-like condition and yielded faint signals that looked like Hawking radiation. While these analog experiments don't prove real black holes behave exactly the same, they strongly hint that Hawking's theory is on the right track. One intriguing avenue of investigation has been the study of gravitational waves, the ripples in space-time emitted when massive objects like black holes collide. When two black holes spiral together and merge, the newly formed larger black hole rings like a struck bell, releasing gravitational waves. Some researchers have proposed that if the event horizon of the final black hole has some quantum structure, instead of being a perfectly featureless membrane, it might cause very slight anomalies or echoes in the gravitational wave signal after the main merger waves have passed. Essentially, instead of one clean fading tone from the ringing black hole, there could be barely perceptible aftertones, quantum echoes hinting that the horizon isn't as simple as classical theory suggests. So far, searches for such gravitational wave echoes have been inconclusive. A few tentative hints have been reported in the data from observatories like LIGO, but nothing definitive that the community agrees on. That isn't surprising, given how incredibly subtle these effects would be, and how noisy astrophysical data can be. But the fact that scientists are actively looking for them shows how eager we are to catch even a whisper of quantum truth from a black hole. It shows that even without clear evidence, we remain determined to test our theories of black holes to the limit. Astronomers have also cast their nets for any direct signs of Hawking radiation itself. Tiny primordial black holes, if any were made in the Big Bang's tumult, could be evaporating now, and their final moments might appear as bursts of high-energy gamma rays. Dedicated searches with gamma-ray telescopes have looked for the sudden flash of a small black hole's demise. So far, none have been convincingly seen. If one were detected, it would be a groundbreaking confirmation that black holes radiate and die exactly as Hawking predicted. The continued absence of such signals doesn't disprove Hawking. After all, those small black holes may simply be extremely rare or long gone. But it adds to the patience required in this field. We may simply have to wait eons, or get much more creative, to directly witness a black hole's last breath. Perhaps the most profound lesson emerging from combining quantum physics and gravity is the realization that space-time might be woven from quantum information. Black holes have become central players in our search for a unified theory of nature's forces. Different approaches to quantum gravity offer different insights. String theory imagines that deep inside a black hole, the singularity may be replaced by a tangle of fundamental strings, a fuzzball with no point-like core, while loop quantum gravity suggests a collapse could bounce into a tiny white hole instead of ending in a singularity. In many of these ideas, the classical notion of an infinitely dense point is replaced by something more spread out and quantum in character. One way or another, black holes seem to demand that our classical understanding of space and time give way to a deeper quantum description. It's as if nature insists that we develop a more fundamental framework, a true quantum theory of gravity, to comprehend what really happens at a black hole's core. For scientists, this means the known laws, general relativity, and ordinary quantum mechanics, are not the final story. There must be a new synthesis that supersedes them under these extreme conditions. Black holes, by pushing physics to its limits, are guiding us toward that new understanding. As we stand at the threshold of this new frontier, it's clear we have far more questions than answers. Will we one day have a complete theory that describes what occurs inside a black hole? A theory that merges quantum mechanics with gravity seamlessly? Will we understand exactly how information escapes, or how space-time itself reacts at the smallest scales? These unanswered questions are the driving force behind much of theoretical physics today, pushing researchers to their creative limits. What is certain is that the journey of discovery is far from over. Black holes, once considered simple endpoints of physics, have revealed themselves to be rich and complex when examined through the lens of quantum theory. They evaporate, extremely slowly but inexorably. They challenge our notions of time and causality. They force us to rethink the nature of information and the very fabric of reality. In exploring black holes, we have repeatedly found that what we thought were limits were only gateways to deeper understanding. In the soft whisper of Hawking radiation, that faint glow at the edge of darkness, we sense that black holes are telling us something profound about the universe. They are urging us to look closer, to unify our understanding of physics, to seek the hidden connections between the very large and the very small. And as we heed that call, we find ourselves on the brink of new horizons of knowledge, where answers to these paradoxes may eventually shine. Black holes thus hint at secrets that could unify our view of nature. For now, as we let our imagination wander, we see the black hole not only as a destroyer, but also as a transformer, a cosmic alchemist turning matter into energy, order into chaos, and perhaps chaos back into order in ways yet to be understood. Every particle or photon that has fallen into it may still resonate within, its quantum echoes whispering through the fabric of space-time. Those faint echoes could, in theory, re-emerge someday, perhaps eons from now, as subtle patterns we have yet to recognize. In this sense, black holes are not truly the ultimate endings they appear to be. They are enigmatic chapters in a cosmic tale still being written. Our exploration of the mysteries within black holes has led us from the stretching of time and warping of space to the very edges of reality, where quantum effects come into play. We have peered into darkness and found that it isn't absolute. There is a glimmer of insight, however faint, suggesting that even a black hole's abyss may eventually give up its secrets. The story of black holes, it turns out, is not just about destruction, but also about transformation and revelation. It has forever changed our perspective on these cosmic enigmas. As we conclude this part of our journey, the black hole remains as compelling as ever, a teacher of humility and wonder. It guards many secrets, but each year we chip away at the ignorance, guided by theory, observation, and an undying curiosity. The tapestry of understanding is still incomplete, missing threads where quantum mechanics and gravity intertwine. But we will continue to weave those threads, one discovery at a time. Black holes were once purely theoretical, dark monsters lurking only in calculations. But now we have tangible evidence of their reality. In 2019, humanity captured its first direct glimpse of a black hole's silhouette, the glowing ring of hot gas around the shadow of the supermassive black hole in galaxy M87. That remarkable image, assembled from a global network of radio telescopes, showed a bright, lopsided ring framing a circular void. It confirmed that these objects are real and as mysterious as we imagined. Seeing a black hole's shadow, essentially seeing where light is missing, was a profound moment, turning a concept into something almost tactile. Yet, as awe-inspiring as that first image was, it only deepened our questions about what lies beneath the veil of the event horizon. And so, even as we leave the immediate vicinity of the black hole's horizon and all the enigmas it contains, we carry with us the profound lessons it has taught. The adventure does not end here. Beyond the horizon of our current knowledge lies more uncharted territory, perhaps puzzles about how black holes shape galaxies or how they fit into the grand cosmic cycle. Our voyage through the Maelstrom prepares us for those final frontiers, reminding us that in the grand sweep of exploration, every ending is but a new beginning in disguise. The next chapter of discovery awaits, pulling us onward into the unknown.